All right. If you haven't, you need to check in. People are still not checking in or checking in way late. Please do that. All right. Today, there's a couple of things I want to go over. First, I want to review a little bit about what's on your screen, so what we did last week. Then I will go over questions on W2, and then we'll work into summation notation and newer stuff. Okay. Um, so first, before we get to questions on W2, I want to just kind of lay the groundwork of what it actually is. So last week we went over definition of a sequence. There are two different types of sequences. There are infinite and finite. And a sequence is just any list of numbers that can be ordered in a pattern. Okay, so it has a first term, it has a second term, a third term, an nth term, and then if it's an infinite sequence, it just keeps going. Okay, if it's a finite sequence, it just ends at some number of the term. There are different types. They're explicit sequences, which are just defined by a specific pattern. So there's a direct equation for every single term, right? So you don't need any terms in between. You can just pick the number of the term that you want, plug that number in, and get the actual term itself. All right. So I have an example up there, an, right? If you can write a rule for the nth term of a sequence, then it's explicit. And then there are recursively defined sequences, such as the Fibonacci sequence, which a recursively defined sequence is a sequence in which every term is made up of terms previous to it. Okay, so what the Fibonacci sequence says is that the kth term, so some number of the term, is the sum of the two terms previous. So a k minus 2, that's two terms previous. A k minus 1, that's one term previous. Okay, and then we went over factorials as well. So the definition of factorial, n factorial is 1 times 2 times 3 times 4 all the way up until n. Okay, so for example, 5 factorial, that's 1 times 2 times 3 times 4 times 5. Okay, so that's what we covered. Your homework was W1 and W2. W1 was over kind of explicit sequences where there was a specific pattern and you just kind of had to fill in the blanks. Okay, and then W2 was over recursively defined sequences, which we'll kind of get into here in a second. Okay, so before we go into that, are there any questions about what's on your screen? All right. So on the left, that's W2. I jumped a couple of levels. So this is in the 64 range, which where I'm guessing is where people start to have a little bit of problems. All right. And remember, recursively defined sequence is a sequence in which every term is made up of terms previous to it. Okay, so on this problem, it says find A3. I'll zoom in just a little bit. It says find A3, A4, and A5. And we're given A1, A2, and the rule for AN. Okay, so what this rule says is that AN, the nth term, is the sum of the term just before it. So the term before n, that's AN minus 1. And then a term before that, which is AN minus 2. Okay, so our third term is A3 minus 1 plus A3 minus 2. And then we can simplify those subscripts just a little bit into A2 plus A1. Okay, and then we just plug in what A2 and A1 are. So A2 is 1, A1 is 1, so that's just equal to 2. Again, the subscript notation is I'm guessing, is where people are kind of struggling with this. That's the number of the term. N minus 1 is the term before n. N minus 2 is 2 terms before n. Okay, A4 is equal to A4 minus 1, so the term before the fourth term, plus 2 terms before the fourth term, which is A3 plus A2. A3 is 2, which we just found. And then A2 is 1. So the fourth term in this sequence is 3. And then the fifth term is the sum of the term before the fifth term plus the term 2 terms before the fifth, which is equal to A4 plus A3. A4 is 3, which is what we just found. And then A3 is 2. So this is equal to 5. Questions over how I get any of that? How do you know what A is equal to? A is just a placeholder. A is the number of the terms. So like A5, that's the fifth term in the sequence A, right? Think of it as function notation. So A5 is kind of like f of 5. Right? We're not solving for f here. We're solving for the fifth term. Right? A3, we're not solving for A there. We're solving for the third term. That's what A3 means. Okay, so we'll do another one. In this, we are given, so we're asked to find A3, A4, and A5, given A1, A2, and the term AN, right? So the nth term. And we want to find A3, A4, A5. Okay, so the first term is 3, the second term is 5, and the nth term is 2 times the term before the nth term plus 2 times the term before, or 2 terms before that. Okay, so if we just substitute in A3, a3 is equal to 2 times a3 minus 1 plus 2 times a3 minus 2. And we have both a2 and a1. So we just substitute those in for what they're actually equal to. So that's equal to 2 times 3 and 2 times 5. Which is 14. So the third term in this sequence is 14. And then we do that for a4 and a5. All right, so a4 Okay, so the fourth term is 2 times the third term plus 2 times the second term. So that's 2 times 14 plus 2 times 5. 2 times 14 is 28 plus 10, that's 38. And then we do the same thing for the fifth term. All right, so the fifth term is the sum of a4 plus a3. So that's 2 times 38 plus 2 times 14. So we get 104. Okay. Questions about this before I actually enter this and then we move on? Okay. So all of this isn't like specific. I want to know exactly where you're having trouble with this. Um, I personally don't think we're going too fast. This recursively defined stuff is just summing terms before the term that we're looking for. Okay, so again, our initial rule here is just summing two terms before. Again, all of it isn't. I we need to be like really specific when we're asking this, so I can actually help you out. All of it that's we haven't gone over very much. We're just getting patterns and defining them. So like where on this problem are you struggling? That's what I want to know. I don't. So what you plug in for the subscripts is given by this rule. Okay. So an, the nth term, so the term that we're trying to find. So in red, we're trying to find a3. We're trying to find the third term. In blue, we're trying to find the fourth term. In green, we're trying to find the fifth term. Okay, so for the third term, we just replace n with 3. Right? So when 3 is n, we'll replace that everywhere we see n. So then 3 minus 1 on this first one, that's 2. So 2 times the second term, then that becomes 3 minus 2, that's 1. So that's 2 times the first term. And then we have a2 and we have a1, right? So then we just replace those with that. This is all really just a little bit more, it's more like substitution than anything. So when we did function notation, that was just substituting in, right? Whatever we saw in for x, we would substitute that in, right? So if f of x is 3x plus 2, and we were trying to find, in this case, like the fourth term, we would substitute in 4 for x. It's the same thing. Right? So a3 is really just like f of 3. And 2, a3 minus 1, that's, again, we just plug in that 3. So we'll do one more. Oh, I just added wrong. All right. All right, a1. A1 is 2, so the first term, no matter what, is 2. That's just defined. We're given that. The nth term is defined by this rule, so 6 times the term before what we're talking about. Okay, so a2, again, we just replace 2 wherever we see an n. So that's 6 times a2 minus 1. And a2 minus 1, if we simplify that subscript, that's just a1, right? And then a1, that's just 2, so 6 times 2 is 12. So our second term is going to be 12. So questions on the second term. Okay, so then we find the third term. And the third term is 6 times the term before that. So we get 72. Questions on finding the third term? All right, then the fourth term. So we're doing the same thing. How did you get 6 times 12? Okay. So A3, the third term, is 6 times the term before it. So that's 6 times A2. A2, the second term, is 12. So it's 6 times 12. That's 72. And again, we do the same thing for the fourth term. So that's 6 times the term before it. So questions on how we found any of that? Okay, so that's all you're doing. You're just adding terms previous to the term you're trying to find. Okay, so let's move on just a little bit. All right. So back to what we were doing last week as well. All right, so we covered explicit sequences and sequences and recursively defined sequences. Okay, we also went over factorials, which I want to do a really quick example of, and I kind of already have it written out for you, but just pretend like I didn't. All right, so an example that I would expect you to be able to do is n plus 2 factorial over n plus 4 factorial. By definition, n plus 2 factorial is every number up until n plus 2, right? So think of a number line. And it's all of those numbers multiplied together. And the same thing for n plus 4. Okay, so that's just replacing those factorials with what they're actually equal to. Okay, so all we did was, again, was substitute. And then we can cancel out common terms. Okay, so on the top, everything up until n plus 1 and n plus 2 cancels out all the same on the bottom. So we're left with 1 over n plus 3 times n plus 4. Questions about that example? Yeah, so you can cancel out the common terms. Yeah, I mean it's besides the actual definition of what a factorial is, everything is exactly as you've done before. Right? So ones cancel, twos cancel, threes cancel, fours cancel, all the way up until n plus 2. And the only difference is in the denominator, those n plus 3 and n plus 4. There's nothing in common with that in the numerator, so they stay there. Okay, so again, it's just multiplication. It's just fraction stuff. Okay, and one quick note on factorials, they do follow order of operations. And it's kind of on the same uh, tier as exponents, right? So 2 times n factorial does not equal 2 times n and then that factorial. Those are two very different things. Okay, so the factorial only modifies what it's directly by. Okay, so if it's only by one thing, it only modifies that one thing. If it's modifying some things in parentheses, then it's modifying just those things in parentheses. Okay, and I'm not too worried. I just want you to know that. We'll kind of go over that again a little bit more in depth a little bit later. But it follows order of operations, kind of the same as exponents. Right. So now, some new stuff. Right. And this is kind of the same thing as sequences. We're just adding one little notation and a concept, okay? And that's summations. So the sum of the first n terms of a sequence, right? So if we have a sequence A1, A2, A3, right? We can sum those together, and the notation to do that is this right here, which is called sigma notation or summation notation. You'll hear me refer to it in both ways. All right, and what this is saying is it's telling you to sum from the first term to the nth term of the sequence A. All right, so I want to go over just a couple of quick things in terms of that notation, and then we'll go over an example. All right, so this I down in the bottom left, that is the index, right? So that tells you what you're looking for. That's kind of like your variable. That's your n in the sequence. The 1 on the bottom right, that is the lower limit. So that tells you where to start. And then the top term, that is the upper limit. So that tells you where to stop. Okay. And then everything else is kind of what we've discussed before. So AI, that's the sequence, where I is just the number of the term. Okay, so what all this culminates in is the sum of the first term, the second term, the third term, all the way up until the nth term. All right, so for example, which might clear some things up, we have the sum from I is equal to 1 all the way up until I is equal to 5 of the sequence 3 times I. So what this means is that we have 3 times 1 plus 3 times 2 plus 3 times 3 all the way up until 5. Okay, so that is sigma notation. That's what that means. Are there questions about anything you see up on your screen? Can you do one for my Excel? They look a little different. I realize they look different. I haven't gone over everything yet. I'm just asking if you have any questions over anything you see on your screen. So we're going to do one more basic example, and then we'll move on to what your homework is actually going to look like. Which again, if you're trying to do that right now, it's going to seem difficult. So just hold on a second. Okay. So in this example, we're trying to sum from k is equal to 3 to k is equal to 6, 1 plus k to the second. Okay, so if we write that out, that's 1 plus 3 squared, right? Our lower limit is 3, so that tells us where to start. Plus 1 plus 4 squared, all the way up to 6. So then we get 16 plus 25 plus 36 plus 49. So the sum of this sequence from k is equal to 3 to k is equal to 6 is 126. Are there any questions over how I got anything up on your screen? K is still the index. Yeah, so it's not always going to be I, it's not always going to be n. Whatever variable is here, that's what we're talking about. Does it matter that does it matter that the variable is changed? No. Anything that's right here and right here, that's your variable. It can be I, it can be A, it can be B. It's just a variable. It's like X. All right. So there's some, like everything we do, there's some properties of these things that we need to know, right? And again, this will help you on the IXL, so just be patient on that for a second, right? 3 properties. All right, we're going to start with the first. And in each of these, if you see a C, that's just some constant number. It's like 1, 2, 3, 4. It's not a variable. It has nothing to do with the sequence. It's just a number. Okay. So in this first property, we are summing from I is equal to 1 all the way up until I is equal to n of some constant number. Okay, and what this means, since there is no variable with our sequence, right, so there is a missing I right here, and since there is none, we're just summing the constant C a bunch of times over, right? So when there is only just a constant, we get C times the number that we're summing. Right, so if we wrote this out, right, so when I is equal to 1, that's, again, it's just C because there's no variable there to manipulate. The second term, again, is just C. The third term, again, is just C. The fourth term is C. So we're just summing C, our constant, a bunch of times. So however many times we sum that, we just multiply that by that, right? So we get the constant times the number of times we're summing it, which is the definition of multiplication. Okay, so if you ever see a summation of just a constant, you're just multiplying that constant by the number of times you're summing it. In the second property, we have the sum from I is equal to 1 to I is equal to n of some constant times our sequence. Right? So if we were to write this out, and what this is actually going to be equal to is the constant times the sum of the sequence. But if we were to write it out, if we were to simplify this, we would get C times the first term plus C times the second term plus C times the third, all the way up until C times the nth term. Okay, and when we do that, we can actually factor out each of these constants. So we just get C times the sum of the sequence. Which by definition, if we're summing that sequence, that's equal to the constant times the sum of that sequence. Okay, so that's why this works. And you're not going to have like specific example of this just yet. I just want to have this in your head for when we get to harder stuff. Okay, and then the third property is this sum from I is equal to 1 all the way up until I is equal to n of two different sequences. And what this is going to be equal to is we can just take each of these sequences alone, all right? Because if we do this, we get the first terms of each sequence plus the second terms of each sequence all the way up until the nth terms of each sequence. And then we can rearrange that. Where the A's are all first. And the B's are all second. And again, we can use our definition of what a summation actually is. To rewrite it. Okay. And again, I'm not so focused on you knowing this step by step right now, but this is kind of setting the stage for later stuff that we do. And this is kind of the start of like actual calculus. Okay, so calculus is the sum of really, really small things over and over and over again, which is all rooted in this stuff that you're doing right now. So when you get to calculus, hopefully next year, you're going to see very, very similar rules for derivatives, for integrals, and everything you do from there on out. So these rules can be reflected into calculus. So if you really understand these, it's going to make your whole life a whole lot easier in the long run. Okay. I'm not going to go over like specific examples of this just yet, but I want this in your head for later on. And if you haven't written this down, I strongly suggest it, because this is super important for later stuff. Okay. I don't want to focus on it right now, but I want you to start to think about it. Okay. So, I'll give you a second if you need to kind of catch up. And then we'll do an example of what you will actually see on the IXL, and then you guys can get to work. Okay, so we've kind of already gone over this, so I don't want to spend too much time on this. I don't think you need to write this down. And if anything, you need to write down this kind of second step. What a series actually is. So a series is the sum of a sequence. That's pretty much all it means. And there are two different cases. There's finite sequences, which we've been dealing with. Okay, so that's just the sum of some finite sequence. And then there are infinite sequences, right? Which are sums of sequences that don't actually stop, right? So it starts at the first term, but it never stops at the nth term or ith term or whatever. It just keeps going. Okay, and there's kind of important distinctions for both. Normally, finite sequences always converge, and then sometimes infinite sequences converge and diverge. that's not important right now. You just need to know that there are two different types. There's finite and infinite. Finite sequences are normally called the nth partial sum. Um, so like if you're trying to find the sum of 5 terms of a sequence, that's the fifth partial sum. And you'll kind of see that in the next example. Okay. Again, I'll give you like a couple of seconds to actually catch up on writing this if you want to. Um, Again, we've kind of already gone over a definition of what this actually is, except for the infinite sequence. So that's probably, that second part right there is probably the new stuff. Okay. So on your homework, which is W10 on IXL, and actually we can skip this part. You're going to get problems that look like this. All right. So this is actually two problems just condensed. So the top, it gives you the summation from n is equal to 1 until n is equal to 63 of the constant negative 29. So the first thing that's going to ask is this finite or is this infinite? And if this number is just a number, then it's finite. If it were to be the infinity symbol, then it'd be infinite, right? And then it asks for the number of terms, right? So you don't actually subtract these two numbers, which is probably what some people might be thinking. So you don't do 63 minus 1. You just count from 1 to 63, and there are 63 terms. All right, so that's really all it's asking up until like 75. Okay, a second example of this. We want the sum from n is equal to negative 1 all the way up until 71, right, of 2n minus 4. And again, the first question that they're going to ask is it finite or infinite? And again, our upper limit and our lower limit are both numbers, so they're finite. And then it asks for the number of terms. Now, if our lower limit was 1, we would have 71 terms. But it's negative 1, right? So on our number line, we know from 1 to 71 is 71. But there's a 0 term now and a negative 1 term. So we're adding 2 terms. So we get 73. Okay, so we have to be careful about where our lower limit is actually starting. And then later on, and I think this starts about 75 or 80, it starts to ask a question like write the series using sigma notation with the lower limit of some number. And the first thing we need to do is to get the actual sigma notation correct. Right? So our lower limit is going to be n is equal to 1. And our upper limit is just how many terms we're working with. So negative 2 is our first, 1 is our second, 4 is our third, and then 7 is our fourth, and 10 is our fifth. So we're dealing with 5 terms, which mean our upper limit is just 5. So that's the first step. That's kind of the easy part. And the next part is what goes in parentheses. Okay, and for that, we need to find a rule for this sequence. Now, in order to do that, we have to find the pattern and then put that into mathematical terms. Okay, so we know that the difference between each of these is 3. So when you see a difference like that, you know where you're going to be multiplying by 3 of some kind. So if we just do 3n at first, that might seem like a good rule. And then we have to check it. So 3 times 1 is 3, but it should be negative 2. Right, because that's our first term. So then we have to modify it. Okay. In order to get to negative 2 from 3, we have to subtract 5. And then we can check it for the second and third term. And it all checks out. Okay, so this will be the hardest part. Finding an actual rule for the sequence, and then checking it. Okay, but for this problem, this would be your answer. Okay, this will be difficult, especially like that last part. The first part should be decently easy, so long as you actually understand how the lower limit and upper limit work. Okay, once we get to like 75, then it'll start to get a little bit harder. But this is good practice for actually finding rules of a sequence and then being able to put that into math terms. Okay, and I realize we're kind of running out of time here. This will be up, so if you are struggling with finding the rule of a term, that's kind of like a good rule of thumb, a good basis to start. All right. So I'll leave this open for like a minute or two, and then I'll head over to Teams if you have more specific questions. But if you have more general questions, now would be a great time to ask. If there are none, then I'll end it. All right, so I'm going to close this. I'll start a meeting on Teams if you have specific questions, and I'll see you there.